Good morning, everyone. My name is Yondela Norman, and I'm an MSc candidate in Rose University. Today, I'll be talking to you about my research findings, whereby I examined the modification of the Subtropical Thicket Restoration Program Planting Protocol and its influence on Portulacaria afra survivorship integrated arid thicket. For the last 150 years, the Albany thicket biome has undergone extensive degradation, owing largely due to overstocking of livestock, particularly goats. The arid forms of this biome are especially vulnerable to this type of degradation, as the goats browsing from the bottom up takes away the lower branches which are vital for providing shade and organic matter to the soil. What happens as a result is the conversion of what used to be a densely vegetated and biodiverse habitat into a severely degraded pseudo-savanna. Because arid thicket types cannot recover autogenically from disturbance and degradation, active measures have to be implemented in order for restoration to be successful. Therefore, the South African government initiated what is known as the Subtropical Thicket Restoration Program, which is aimed at achieving this goal. The planting protocol involved using unrooted Portulacaria afra or spekboom truncheons and planting them in degraded thicket patches. However, because these thicket patches were characterized by capped soils with little to no infiltration and high soil temperatures, the survivorship of these unrooted truncheons did not exceed an average of 50%. Therefore, the aim of my study was to modify the current planting protocol used to rehabilitate degraded thicket as a means of not only increasing the survivorship of Portulacaria afra, but also as a means of fast-tracking the rehabilitation and restoration process altogether. Which brings me to my research questions. Firstly, do nurse plants create ideal conditions for the establishment and growth for spekboom cuttings? What influence will companion plants have on the survivorship of spekboom? To what extent does limited watering enhance survivorship of spekboom as well as its growth? Are scarification and herbivorous simulations potential aids in unrooted truncheons in terms of aiding in the establishment and growth? And what influence does a modified planting protocol have on the photosynthetic efficiency of Portulacaria afra and the soil moisture content and temperature of the pondings in which they are planted? My study area was in a communal farm known as Chinugunu, which is situated in the western Baviaanskloof of Heartland. The study site falls under what used to be known as Groot Arid Spekboom Veld and has now been reclassified as Sunday's arid thicket according to the updated national vegetation map. As you can see from the drone shot to your right, the thicket in this area has been severely degraded owing due to decades of overstocking of livestock, especially goats, as was mentioned before. Now, the first treatment I'm going to talk about is that of the watering regimes. This treatment involved the construction of 120 pondings, each of them containing 3 rooted spekboom cuttings. Now, out of these 120 pondings, 30 of them served as the control, where they would have no brush packing with them, while the remaining 90 were brush packed with Vachellia carew branches. Out of these 90 brush packed pondings, they were divided into 3 groups of 30. The first group was watered with 2 liters of water once a month. The second was watered twice a month, or at least every 2 weeks, and the third group was watered every week. The second treatment involved the use of companion and nurse plants as a means of enhancing spekboom survival. With the companion plants, the pondings were constructed in a similar fashion as to those of the watering regimes, except these 3 spekboom cuttings in the pondings were planted along with Lycium ferocyssimum, Rhagosum obavatum, and Aloe ferox, which are locally indigenous shrubs and succulents that were found in the degraded study site. Now, with the nurse planting treatment, the pondings were constructed underneath Carissa hematocarpa canopies, and the spekboom were planted within said pondings. Now, much like the companion plants, controls, and the monthly treatments from the watering regimes, these pondings were also watered once a month as a means of giving the spekboom a head start and a means of buffering them from the harsh elements of the degraded thicket. Now, the next treatment I'm going to talk about is that of the unrooted truncheons. In this treatment, unrooted truncheons were used and were planted inside pondings that were constructed inside the study site. These truncheons underwent various pre-planting treatments, such as scarification as a means of creating more sites of root formation and growth, as well as herbivory simulation, which involved cutting off the apical meristems of the unrooted truncheons as a means of encouraging the skirt-like form of the spekboom that we often see in restored and intact thicket. As you can see from this slide, these are the unrooted truncheons and the various pre-planting treatments to which they were subjected. First was the scarification treatment, the scarification plus the herbivory simulation treatment, the herbivory simulation treatment on its own, and the control, which was just planted in the pondings as is. We also looked at the ecophysiological data that arise from these planting protocols and see how they were influenced by these planting protocols. For this particular chapter, we divided the treatments into 4 different groups, namely the pondings underneath the nurse canopy, pondings underneath Vachellia carew canopies, pondings that were constructed in open areas, and pondings that had companion plants with them. The ecophysiological data and variables that we measured were as follows: the soil moisture content and soil temperature of the pondings, the photosynthetically active radiation within the pondings, as well as the chlorophyll fluorescence of the spekboom leaves within those pondings. As for data analysis, for survivorship of Portulacaria afra, we assumed that all data was normally distributed, and we tested for this assumption using Shapiro-Wilks test. For the survivorship, we also used a single factor ANOVA to test for statistical significance. For the ecophysiological data, we used a repeated measures ANOVA followed by a post hoc Tukey HSD to test for statistical significance. And now onto the results. For the watering regimes, as you can see, the weekly plantings or the weekly watering regimes had the highest average survivorship of spekboom, followed closely by the control, then the monthly watering regimes, and the bi-weekly watering regimes. Now, the reason why the bi-weekly watering regimes had a lower survivorship than that of the monthly watering regimes remains unknown and unclear. And that's something that warrants further investigation as to what influence water inputs, whether they be increased or decreased, would have on overall spekboom survivorship and overall establishment. However, with the weekly watering regime, because of the increased water inputs, the spekboom had even more water resources and were better buffered from the drought, which then contributed to their high survivorship. The control was surprisingly higher, as we initially assumed that because they had no brush packing, they'd be more vulnerable. The pondings, or the spekboom rather, that were in those pondings without any brush packing would be more exposed to the elements as well as herbivory, and less of them would survive. With regards to the companion and the nurse planting treatments, we found that the companion plant had the highest levels of average survivorship, mostly owing due to the facilitation process that the companion plants provide to the spekboom cuttings. The nurse planting treatment had a lower average survivorship compared to both the companion planting treatments as well as the control, and we suspect that's most likely because of competition between the nurse plant and the spekboom cuttings for nutrients and water and other vital resources. Nevertheless, it still has a high survivorship, and the benefits of nurse planting far outweigh the costs. Now, it should be noted that while the companion planting treatment yielded highest average survivorship of spekboom cuttings, the same can't be said for the companion plants that were actually used. For instance, none of the lycium or the rhigosum survived throughout the course of the study, and the only remaining companion plant species that did survive was the aloe ferox, Even still, it had varying degrees of health status, where 33% were alive and well, 26.7% were highly stressed, and 40% were dead. This variation in health and overall survivorship of Allophorox could be attributed to the fact that the Allophorox as a plant species is highly susceptible to a wide range of diseases such as alloscale, allocancer, and infestation from ants and aphids, and this likely could have contributed to such a variability in its overall survivorship. Now, with the unrooted truncheons, we found that the control had the highest levels of average survivorship, owing largely due to the fact that it underwent the least stress out of all the truncheons that were subjected to pre-planting treatments. This is followed closely by the herbivorous simulation treatment at 74.9%, and this is likely because if the simulation actually encouraged further growth, as what would be observed from spekboom in intact thicket when they are browsed from the top down by indigenous herbivores. With the scarification treatment, while it creates more sites for root development and growth, it also creates even more wounds and more sites for water loss, and this could likely explain why this treatment had a relatively lower survivorship compared to the herbivorous simulation and the control. The herbivorous simulation plus scarification treatment had the least, or the lowest rather, average survivorship of spekboom, and this is likely because of the compounded stress of the scarification, which creates even more sites for water loss and desiccation, as well as the added stress from the cutting off of the apical meristem. Now, when looking at soil moisture content and soil temperature, we can see that the pondings underneath the nurse canopy had a much higher average soil moisture content compared to all the other treatments. In fact, it had the highest average soil moisture content while also having the lowest average soil temperatures. And this is due to the protection that the nurse canopy provides to the pondings and its contribution to the amelioration of the local climate. Now, with the pondings underneath the Vachellia Karoo canopy, you can see that they had the lowest average soil moisture content while having the second highest average soil temperatures. A possible explanation for this is that because the Vachellia Karoo as a species is a highly competitive pioneer species, it ends up competing with the spekboom cuttings for water and other resources, which probably explains why the soil moisture content is relatively lower. In terms of when looking at the pondings within the open area, you can see that the open area had a much higher average soil moisture content throughout the course of the day compared to the pondings in the Vachellia Karoo canopy. Again, this is likely because whatever the available moisture within the pondings was only utilized by the spekboom, and they didn't necessarily have to compete with other species for that available moisture. But as expected, the pondings within the soil temperature had the highest, the pondings within the open area had the highest average soil temperature because they were exposed to the elements throughout the course of the day. When looking at the pondings within the companion plant, as well as spekboom that were planted using the current planting protocol where no pondings were involved, you can see that pondings within the companion plant had a much higher average soil moisture content and lower soil temperatures, most likely because the pondings not only helped store available moisture, but the storage of said available moisture helped mitigate and slightly reduce the average soil temperatures. The soil around which the working for water spekboom were planted had a much lower average soil moisture content and a much higher average soil temperature. And this is likely because no pondings were involved, and therefore the spekboom or the soil around which it was planted was still highly degraded and very inhospitable for spekboom. When looking at the photosynthetically active radiation in pondings above and below canopy, you can see that above canopy, the companion plant had the highest PAR, followed closely by the open area, the Vacilla canopy, and the nurse canopy. But below canopy, it's a different story, whereby the nurse canopy had the lowest, PAR or light infiltration, followed then by the Vacilla canopy, the companion plant, and the open area, pondings. Again, this is likely because the dense vegetation and the dense foliage of the nurse plants greatly limited light infiltration below the canopy. And much of the same can be said with regards to the Vacilla canopy, where light was or the light infiltration was limited by the biomass of that canopy. Below canopy, the open area had the highest PAR, most likely because they were exposed to daylight or exposed to light infiltration throughout the course of the day. Companion plant pondings had a relatively lower average PAR below canopy, and this is likely because the pondings were situated in areas of varying levels of shading, which likely could have influenced those results. Now, when looking at the chlorophyll fluorescence, one can see that within among the treatments, the Portulacaria afra cuttings had the highest chlorophyll fluorescence, or the highest levels of maximum fluorescence underneath the nurse canopy, followed closely by the cuttings within the Vacilla canopy, cuttings planted in open area pondings, and cuttings that were planted with companion species. The spekboom cuttings underneath the nurse canopy enjoy much needed protection from the elements and herbivory, as well as protection from photoinhibitory damage, while also at the same time enjoying or benefiting rather from the ameliorated microclimate underneath the canopy. Hence why they have the highest photosynthetic efficiency amongst all the spekboom across the different treatments. Much of the same can be said for the spekboom cuttings underneath the Vacilla canopy. As well, the canopy of the Vacilla may not be as densely vegetated as that of the nurse canopy. The spekboom cuttings still enjoy much of the same benefits. The cuttings planted in the open area were slightly lower than those within the Vacilla canopy, and that could also be a result of them having access to sunlight for a much longer period of time compared to the cuttings that were planted underneath canopies. The companion plant, oddly enough, had the lowest maximum fluorescence out of all of them, and again, as mentioned in terms of the PAR below canopy, this is likely because the companion plant plantings were done in areas or constructed in areas where there was variable levels of shading, and again, this could have likely influenced the results, but this is something that warrants further investigation. So based on these results, we can conclude the following. The construction of pondings aids in Portulacaria afra establishment, as the final survivorship in each treatment was well over 50%. The inclusion of post-planting irrigation of at least once a month over 3 months further assist in Portulacaria afra establishing itself. Although companion planting produced high levels of survivorship of spekboom, the efficacy of this method warrants further investigation due to the high mortality rates of the companion species used. In comparison, however, the nurse planting treatment is a more reliable approach to planting spekboom in degraded thickets, as the nurse plants would ideally be already well established and therefore have a lower risk of mortality. This is justified by the fact that none of the nurse plants died throughout the course of the study. While using unrooted truncheons has proven to be feasible, it's ideal to plant them in a ponding during early spring along with post-planting irrigation to give them as much time as possible to strike roots as possible under milder spring conditions. In general, the planting protocol used in the study ultimately achieved the primary objective of improving Portulacaria survivorship to at least 50%. Now, with these conclusions, there are recommendations that go with them, namely, the construction of pondings being a very useful technique in creating conditions favorable for spekboom survivorship and growth. The second recommendation is that in the presence of a game fence, spekboom can be successfully planted in pondings without the need to brush pack, as the game fence, while it may not necessarily eliminate the threat of herbivory, it can still greatly limit it to the point that spekboom survivorship can be enhanced. Nurse planting, particularly underneath a Carissa hematocarpa canopy, is a potential game changer for spekboom propagation as the cuttings benefit from the protection and microclimate the canopy provides. Companion planting is a method that requires further investigation on facilitating the improved survivorship and growth of spekboom. Further research, therefore, is needed to investigate ways to mitigate transplant shock for the companion plants that are to be used. Alternatively, one can use local succulent companion plants for the rehabilitation of degraded Albany thicket, as there's less aftercare required due to the hardiness of said succulents. As you can see here are my acknowledgements and everyone who's helped made this research possible. And here's my reference list. Here's the rest of it. Thank you all very much.